All right, so today, all right, we're going to kind of generalize things just a little bit more. So the one kind of specification that our Maclaurin polynomial required is that our function was trying to approximate at 0. Okay, we're trying to approximate the transcendental function, be it e to the x, be it sine of x, and we are always trying to be centered at 0. Okay. But what if we don't want to try and center at 0? What if we want to try and approximate at a different value, right? Well, we need to make some adjustments here, right? Because this is only for 0. How do we then adjust for being centered at 0? Well, I mean, in a similar sense to how you transform a function, right? To shift things, right? If we want to center at a different x value than 0, we want to shift things horizontally, all right? To shift things horizontally, what do you do with your x values? Well, you take your x value, okay, that you normally had. So normally these were x's, right? And you then subtract your c, where you're centering. So x minus c, x minus c, x minus c, okay? And we create then a new thing now called a Taylor polynomial, okay? And a Taylor polynomial is like the more general version of the Maclaurin polynomial, okay? So a Taylor polynomial is what we use here. You'll see the same exact kind of, like they're very similar kind of, properties here, right? There's f of c, right? Whereas before it was f of 0. We were centered at 0 for the Maclaurin. Now we're going to be centered at some value c, so it's f of c, right? And then it's f prime of c times not just x now, but x minus c. Why? Because we're doing that transformation, that function transformation to the Maclaurin where we're shifting things left or right depending on, where our c is. Okay, so there's that x minus c. And then it becomes f prime prime of c all over 2 factorial, right, times x minus c squared, and so on and so forth, right? So all we did here was take our Maclaurin, okay, and rather than using 0, rather than being centered at 0, now we're centered at some generic value c, so all those zeros get replaced with c's, and all these x's, we're transforming them, minus c, whatever, it's shift left or shift right. So it's x minus c squared, x minus c cubed, x minus c to the 4th, so on and so forth, okay? So, like I said earlier, a Maclaurin polynomial is just a specific type of Taylor polynomial with c equal to 0. Okay? So let's take a look here at an example of how we can then use this third degree, or how we can use Taylor polynomials to approximate functions. Okay? So find a third degree Taylor polynomial for f of x equals 2 sine x centered at the following value. So we're going to come up, we're going to build a polynomial that's going to approximate the curve 2 sine x and centered at different values, okay? So we're going to build from different x values, right? So first we'll start with c equals 0. And for c equals 0, what kind of polynomial can we actually use here? The Maclaurin, right? We don't need the Taylor because it's centered at 0, so we can use Maclaurin. Okay, so we don't actually need to use the new thing that we learned. You can use the Taylor polynomial thing here. It's just anywhere you see a c, it'll be 0, okay? My recommendation, before you start trying to actually, I guess jump into the work, or at least for your first step, I'd really recommend that you get in the habit of kind of writing out what this general format's going to be, okay? So for example, this polynomial of degree 3 that we're looking for here, right? The first part's going to be f of 0 plus f prime of 0 over 1 factorial x to the 1, right? Okay, plus f prime prime of 0 over 2 factorial x to the 2 plus f prime 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 of 0 over 3 factorial x to the 3. Okay, so that's kind of our setup, right? What do we still have left to do here? What do we need to evaluate? What do we need to kind of plug into this thing? We need to find what f of 0 is. We need to find what f prime of 0 is. We need to find what f prime prime of 0 is. We need to find what f prime 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 of 0 is. All those values, okay? And that's it, okay? So we'll go ahead and do that here. So, okay, if f is equal to 2 sine x, then f prime and f prime prime and f prime 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 will be what? And you guys go ahead and figure those out. Take 30 seconds there and do that real quick here. And if you feel like you got the derivatives, go ahead and evaluate them too at the appropriate point, right? So if you feel like you've got those derivatives, you're feeling good about them, go ahead and evaluate them at the appropriate point and get those values. So, should have gotten values like that, right? F is 2 sine x there. F prime will be 2 cosine. F prime prime will be negative 2 sine. F prime 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 will be negative 2 cosine then. And evaluating all those at 0 because why? Why are we evaluating at 0? C is 0, right? C is 0, right? We're centered at 0. So we're going to use 0 as our center, right? And so we're building this polynomial about that value at 0. So it's like the best approximation are going to be values close to 0, right? The closer we are to 0 when we try to approximate, then the better it'll go for us. Okay. And so now we'll put some pieces in. But since we have some zeros here, right, some parts are going to not, really be around. For example, f of 0 we know is 0, so that kind of just goes away, right? It's equal to 0, so it goes away, right? F prime prime at 0 will also equal 0. So here f prime prime of 0, this is also equal to 0. So this whole term is going to just cancel away. It goes away, right? Because it's equal to 0, so we're going to multiply something by 0, it's still 0. And so that leaves us really just with, well, 2 terms here. F prime of 0 is 2, so you can leave it as just 2 over 1 factorial if you like, x to the 1. And then f prime 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 of 0, we said was negative 2, so it'll be minus 2 over, and again, you can just leave it as 3 factorial, don't need to simplify, x to the 3rd. Okay? And this polynomial then, right, will closely, or, is an approximation of that 2 sine of x, okay, near x equals 0. And so that is our 3rd degree polynomial there. So there's our polynomial approximation. Okay, and let me see here if I can get a good 2 sine x, and then 2x minus 1 excuse me. Okay, so if we take a look at this, so there's sine 2x. Or sorry, it's 2 sine of x. And there's our polynomial. Do you see that? So let me kind of highlight that maybe in a different color here. We'll do not color. I'll thicken the line now. Okay? So again, there's 2 sine x. Okay? And so here's 0, right? We're trying to build this polynomial to match the behavior of 2 sine x right around 0. And look at that. Right around 0, we are pretty doggone close there. I mean, you can see how close we are to the actual 2 sine x. Okay? And again, as we iterate this, as we do more and more steps, the closer and closer our polynomial will, get to that graph of 2 sine x. Okay, the more steps we do. All right? So let's now center it at a different point, though. C equals pi over 6. So this polynomial we're going to create, it will be what kind of polynomial? What will be its name? Taylor, right? Now we got to use Taylor. Okay? But again, all it is a transformation of Maclaurin, okay? So while Maclaurin, and I'm going to use the P sub 3 again, so while Maclaurin asks us to do f of 0, we're now going to do f of pi over 6, okay? And also where we had f prime of 0, we're going to do f prime of pi over 6 over 1 factorial, but then our x, oops, I'm off the screen, there we go. Our x, though, right, we're shifting everything to transform to the right, pi over 6. So we need to have x minus that pi over 6 there to get the transformation, right? We're shifting things over to have a new center. when you have a shift, a horizontal shift, you just take your x value and you subtract whatever. If you're going to the right, you subtract your value. If you're going to the left, you're going to, add your value kind of thing. Okay? Certain number of units. So x minus pi over 6, and then the next one will be f prime prime pi over 6 over 2 factorial, x minus pi over 6 quantity squared, and then plus f prime 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 pi over 6 over 3 factorial, x minus pi over 6 quantity cubed. Okay, like that. All right. Now, we don't need to go through this whole process again of taking these derivatives because these derivatives are exactly the same as were used before, right? We're still using the same curve, so it's really just a matter of taking f and f prime and f prime prime and f prime 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 and evaluating all those at x equals what? Pi over 6, right? All these now are evaluated at pi over 6 because that's our new center, okay? All right. So sine of pi over 6 is going to be 1/2, but then there's a 2 in front of that sign, so it's going to end up being just 1. Okay. Cosine of pi over 6 is root 3 over 2 times 2 is just going to give us root 3. All right. Sine of pi over 6 is again 1/2, but times a negative 2 gives us now negative 1. And then cosine pi over 6 gives us root 3 over 2 times negative 2 gives us negative root 3. Okay? So now I want you guys to go ahead, take the information right there, and go ahead and fill in the rest of that polynomial. Okay? So go ahead, fill in now, make your Taylor polynomial. All right, don't worry about simplifying any factorials if you don't want to. You can just leave it all in factorial form. In fact, I'm going to leave my factorials unsimplified, okay? But if you want to simplify them, you can. Your choice. Okay, so go ahead and fill in that polynomial now. Fill in and get our answer. Okay. Hopefully I typed no. Messed up. What? Minus 1/2. Okay. So should have gotten something like this. Okay. So they're supposed to be like subtract 1 over 2, subtract root 3 over 3 factorial. And if you did plus negative 1 over 2 factorial, that's fine. Plus negative root 3 over 3 factorial, that's fine there too. And again, this is approximately equal to, right, that 2 sine of x, but now it's going to be close to 2 sine of x when we are near that x equals pi over 6. Okay? So what I've done here on my graphing calculator is I've typed in this new polynomial that's not going to be centered at 0, right? It's now centered about that pi over 6. I even shifted my graph so it's centered now at pi over 6. So if you look there, okay, the middle of the graph here will be at pi over 6, so somewhere like right in here. And so there's that polynomial. Again, you can see like right around in that area, it's very good approximation, right? It's almost indistinguishable from the other curve there. Okay, how close it is. All right. All right, so one more here. Let's have you guys try this one here. Let us see all on your own. So go ahead. C equals 3 pi over 4. Give it a go. All right. It's the same idea as what we just did there. Same idea. Okay. Just be careful, right? 3 pi over 4 is in the second quadrant, so watch your, positive and negatives when you're talking about evaluating, well, sines and cosines, right? Sine's positive in quadrant 2, cosine is negative in quadrant 2. So keep that in mind. Yeah, don't read the times 2s. Mm-hmm.
Wait, it's 1 over 2 for the sine of 3 pi over 4, right?
Right, which is same thing as root 2 over 2.
Root 2.
Root 2 over 2, yeah. Okay. And so there is, there's the answer. You can kind of see it there. But I also then put the graphing calculator there. Okay, that's 3 pi over 4 right there. And again, you can kind of see on maybe if I make the line thicker there. Again, centered at that 3 pi over 4.
Is f prime prime just negative root 2?
S prime prime is negative root 2. Uh-huh. Yep. So 3 pi over 4. There's that center at 3 pi over 4. And again, you can see how good of an approximation we kind of get right in there. It looks almost, again, identical to 2 sine x in that neighborhood of points and stuff. Okay? Questions on anything like that? Okay. Now, granted, again, this function we were talking about here, 2 sine of x, okay, it is a transformation of just sine of x. So we could have just done the Taylor polynomial for sine of x, centered at 3 pi over 4, pi over 6, or 0, and we could have just multiplied our final answer by 2, and that would have worked as well, okay? But, in this case, it kind of makes it work out a little bit nicer when we multiply by 2 first, because then it gets rid of the fractions, like root 3 over 2 becomes root 3, root 2 over 2 becomes root 2, so it makes it a little bit nicer. Anyway, moving on here. All right. So example 4, find the Taylor polynomial p sub 3 for f of x equals natural log of the absolute value of sine x at c equals pi over 2. Then we're going to use that p sub 3 to approximate f of 1.5. So again, we're kind of using the Taylor polynomial for, something that, well, bless you, that is kind of useful, I guess, right? We're gonna center it at pi over 2, and then we're going to use it to approximate 1.5. Now let's just see here. Pi over 2, right? The value pi over 2 is 1.57. So we'd expect then that we should be able to use this Taylor polynomial to approximate 1.5, since pi over 2, where we're centering it, is pretty close to 1.5, right? So we should be able to use it. It should be a decent approximation, right? You wouldn't center it at pi over 2 and then try to approximate at like f of 10 or f of 100, because you're going to be so far from that center that the error is going to just be too much. All right. So again, third degree Taylor polynomial. So p sub 3 of x. This one I'm going to take the time to write out here. So and centered at pi over 2. So our first term is going to be f of pi over 2. Okay, very good. Plus f prime pi over 2 over 1 factorial times x minus pi over 2 plus f prime prime of pi over 2 over 2 factorial times x minus pi over 2 to the second plus f prime 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 pi over 2 over 3 factorial x minus pi over 2 to the third. Okay? So there are all our pieces, and again, it's up to us now just to figure out what f of pi over 2 is, what f prime of pi over 2, f prime prime, and f prime 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 of pi over 2 all are. So go ahead and do that. Okay, I'll get you started there. There's f equals natural log sine of x. And so then f prime will be what?
Cotangent.
All right, okay, very good. Right, so derivative of the natural log of something is 1 over that something times the derivative of what's inside. Derivative of sine's cosine, but then we get cosine over sine, which is really just cotangent of x. Okay, and then what's the derivative of cotangent?
Negative CSE squared.
Negative cosecant squared of x. Okay, very good. And then f prime prime prime, negative 2 cosecant x times the derivative of cosecant, which is
CSE of x times tangent.
negative cosecant x cotangent x, which then would simplify to be positive 2 cosecant squared of x cotangent of x. Okay, that was a fun little memory exercise there, right? And now we'll evaluate all of these at pi over 2. Okay? So what will f at pi over 2 be? 0. Okay, what will cotangent of pi over 2 be? Right, so think about, right, cotangent is cosine over sine. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so it's 0 over 1, just 0. Right? Same thing here, it's going to be a negative 0, which is, again, just 0. And then same thing here. We get, oh, what did I do here? Oh, it's cosecant squared. Sorry, cosecant squared. I'm thinking cotangent again. Cosecant is 1 over sine. Sine at pi over 2 is 1, so it's going to be 1 squared, which is 1, but then negative, so it's negative 1 there. My apologies. Thinking cotangent. This is cosecant. Okay. But f prime 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 at pi over 2 will be what? 0. Okay? So even though we're doing a third degree approximation, only one of our terms ends up showing up, right? F at pi over 2 is 0, so that's going to go away. F prime at pi over 2 is also 0. That term goes away. And f prime 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 at 0 is, or sorry, at pi over 2 is equal to 0. That's going to go away. And so we're left with just one term here, which is then going to be negative 1 over 2 factorial x minus pi over 2 quantity squared. Okay, so there's our approximation. And then let's see here how our approximation holds up. So let's find the actual value of f of 1.5, right? So we're going to actually evaluate f of 1.5, which is, you know, the natural log of the absolute value of sine of 1.5, and then we'll compare it to our approximation, see how we did. Okay, so natural log of math num absolute value of sine of 1.5. Okay, approximately, I'm going to write the whole decimal out. So negative 0.0025081562. 0.025081562. And then let's use our approximation here, which would be negative 1 over, well, 2 factorial is really just what? Yeah, just 1 times 2, so 2. So negative 1/2, and then parentheses x, but our x is going to be 1.5 minus pi over 2 squared. Okay, and I'll write that right here. So p sub 3 of 1.5 equals negative 1/2, 1.5 minus pi over 2 squared, and that's approximately, okay, negative 0.0025060599. Okay. Yep. Say, oh, it's on the screen. Sorry. There we go. Okay, so look how closely we match here, right? That is pretty doggone close. Okay. So point, 1, 2, 3, 4, 5 decimal places match up, and then we're only, so what is that? Tens, hundreds, thousands, 10,000s, 100,000s. So the millions place, we're off by, roughly 2 millions. Okay, 2.1 millions. Okay, so it's pretty accurate. Okay, pretty accurate there. But of course, it kind of begs the question, it's like, well, but in order to evaluate this, we kind of need to use a calculator too, right? But anyway. Okay. So, next one here, 4th degree Taylor polynomial for f of x equals x squared plus natural log x centered at c equals 1. And go ahead, I'm going to have you guys try this one. So go ahead and give it a try. Example 5. See what you can do here. 4th degree Taylor polynomial, right? So make sure, again, I recommend that we set up here. So it's going to be f of 1 plus f prime of 1 over 1 factorial x minus 1. Okay, and then I'll leave the rest there to you. But maybe you didn't even need that. Bless you. I'll also give you the simplified version too if you, did simplify your fractions here. I'll write that out. Yeah, that is it actually. Yes. So you can think of. Oh, okay. You can think of 1 over x as x to the negative 1.
Yeah.
Right? And so then x to the negative 1, you take the derivative of x to the negative 1, just like you would x squared or x cubed. So power out front. So it'll be negative x and then subtract your power by 1. So negative x to the negative 2.
Okay.
And the next one will be positive 2 x to the negative 3. You know.
Okay.
Here, all right. So on and so forth, on down. These are all like derivative kind of thing.
Okay. So the next one will be just 1 over 2x to the third.
It'll be 2 over x to the third.
Yeah. And that wouldn't be negative.
Correct, because you already had a negative coefficient, so then bringing the negative 2 up front. Make it wrong. I know, right? It's like the hard stuff now. It's much easier stuff now. You remember how to take the derivative of 1 over x now? Look at that. You were close. So 1 over x, not quite, close. 1 over x is the same thing as x to the negative 1. What's the derivative of x to the negative 1? That's negative x to the negative 2. And then you'll bring that negative 2 out front into its derivative, becomes then positive 2 x to the negative 3. Subtract it out.
So the 1 is 0, right?
Looking at the wrong problem. That's why I think this is not looking right. That's why. Yeah. Looks good. Okay, yeah. Yes, question. It would be, yes, negative 6x to the 4b. Oh, wait, hang on, sorry. So, okay, sorry. From here to here, this would be positive, because it was negative x to the negative 2, so you bring the negative 2 out. Right, but then you're going to bring that negative 2 out front as well, as part of the derivative. So the 2 will be 0, and then negative 2 times negative 1, making it positive 2 x to the negative 3.
And then would this be
So then that would then switch the sign then to be negative 6 to the negative 4. Uh-huh. Question, Sophia? In the real world, we are in the real world right now. I understand what you're saying. Right. So, my belief is that when, in a real world setting, when you're actually typing this thing into your calculator, the calculator is actually running through iterations of this.
Oh, true. I didn't think about that.
Because this is programmable, right? These operations, multiplication, exponents, subtraction, stuff like that, that's all arithmetic, right? The calculator is a very complex arithmetic machine. Natural order X is not something that's actually arithmetic, it's not something that's actually programmed. How do you actually evaluate that, right? Imagine.
Oh, I'm sorry.
Right.
I have no idea
Yes.
what I'm doing, so it's okay.
I can't say that for sure. I can't say that for sure. But I think that's
Just try to
probably
look at number
use
6 and look at
because
number
we-
A for it, or letter A for it.
It's like similar
Oh,
to
yes, I know how to
No,
do
but
it. I take you back. I take you back.
It's okay, I'm not judging you on that, I'm just judging you, look at the direction.
So when we use this in real life, most likely it's never your law. So why does the ACT test require you to know it? Because they can do
It's not like too difficult, but it's also like I'd rather just use the actual. Cause like the calculator,
right.
there's something like annoying about typing in this into the calculator and
Yeah, I have no idea.
I understand. No, because it's why we make this more complicated and we already have the method of getting this, it gives us a better approximation than what that is, but I understand what you're saying.
Thank you.
I have no idea.
You have a point, but I don't want to shortchange. So that's I don't want to shortchange you guys in preparation for the AP test. Of course, that's something that will show up.
All
So.
I'm trying to do is take pictures.
Okay, so there are our two answers, one without the factorial simplified, one with factorial simplified, and then the fractions simplified as well, right? Okay?
Do you have to do the factorial simplified?
Nope, you can leave. Nope, that's why I have both circled there. Either one is fine.
Looks snazzy.
Questions on any of that? All right. And again, this is supposed to be an approximation, of that x squared plus natural log x near 1. Okay? Near 1. It should be close to match. Alrighty? Oh, yes. Sorry. CC, question. Ariana's got a question. I am so sorry.
For f times 4 whatever,
The fourth derivative of f?
-6.
Okay. Well, I mean, did you
no,
get...
I got -6, but why'd you write it as just 6?
Oh. Because I put minus
Oh.
there in front like that. I just threw it. So yeah, if you did plus -6 over 4 factorial, that's, of course, not same thing. Okay. Any other questions? Thanks for that. No? Okay, let's move on here. We're still going to keep on chugging here.
I feel like this is getting a lot worse.
Not today.
It always
Okay.
does. It always
Not
does.
today. Okay, so
Which example are we going to? This last one?
we're going to finish up through this section. So those are multiple choice though on the other side. So
You're killing me.
am I?
You kill me, Shmuel.
All right. Well, let f be a function such that f of 2 is 4, f prime of 2 equals -3, f n plus 1, so the n plus 1th derivative of f at 2, okay, so the n plus 1th derivative of f at 2 is the same as -2 times the nth derivative of f at 2. Okay, so the next derivative at x equals 2, okay, the next derivative at x equals 2 is equal to, right, next because it's n plus 1, is equal to -2 times the previous derivative, the nth derivative. At x equals 2. Okay, so they kind of like kick us off here. They say, okay, f of 2 is 4. You've got that. F prime of 2 is -3. And then for successive derivatives, right, for the next, sequential derivatives, they will just be -2 times the previous one. Okay, so the original function at 2 is 4. The first derivative of the function at 2 is -3. And then beyond that, f prime prime will just be -2 times f prime. F prime 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 will be -2 times f prime prime, so on and so forth, right? So, letter A, write the first 4 non-zero terms of the Taylor polynomial for f about x equals 2. All right.
So the first two don't stick to that pattern.
Say again?
So the first two don't stick to that.
Correct. And that's why it follows this pattern for all n greater than or equal to 1. We stipulate that. We stipulate that. Okay, so that then we don't have to match the pattern for the first part. Okay, because it's only true for n greater than or equal to 1. Okay, so let's do our normal little thing here. P sub 4, because we're doing 4 terms. All right, and we're centered at 2, so that means f of 2 plus f prime of 2 over 1 factorial x minus 2 plus f prime prime of 2 over 2 factorial x minus 2 squared plus f prime 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 of 2 over 3 factorial x minus 2 cubed plus f prime, fourth derivative of f, I'm not going to write all that prime, 4 factorial over x minus 2 to the 4th. Now, why is it important here that we are centered about x equals 2? If we were centered about x equals 3 or any other point, we'd be in trouble because we have no information about the function at 0, 1, 3, 7, 9, whatever you want to say, okay? We only know stuff about the function at 2, and so it's important that we are centered at 2 here, right? We need them to kind of match up. All right. So then we'll go through our parts here, our steps. We need to evaluate f, f prime, f prime prime, f prime prime prime, and f, well, the fourth derivative of f. Okay. But the good news is we're not given a function. It actually makes things easier for us. We don't need to worry about what that function, is. We don't have to worry about taking its derivative. We're going to go ahead and just evaluate these things at x equals 2. Okay? What is f evaluated at 2? 4, right? It tells us right there. Okay? What's f prime of 2? -3, right? Again, it tells us right there. Okay? But then we aren't told anymore about, we're not told explicitly what f prime prime is, but what can we do to get f prime prime? The previous derivative, right? Because now we're in this step, right? For n greater than or equal to 1, so we now are on the next derivative here. Excuse me. So, -3 times -2, right? The previous derivative, multiply that by -2. Now maybe I'll write that out explicitly here for this one. -2 times -3, that gives us 6. Okay? And then f prime prime prime, it's -2 times 6, so it's going to be -12. And then for f, well, the fourth derivative of f, -2 times -12, so it's positive 24. Okay? And so then we just, again, just plug in our values here. So f of 2 we got was 4. -3 over 1 factorial x minus 2. And f prime prime is positive 6, so 6 over 2 factorial x minus 2 squared. And then we have -12 for f prime prime prime, so -12 over 3 factorial x minus 2 cubed. And then plus 24 over 4 factorial x minus 2 to the 4th. And that is an approximation there for f of x. Okay, yeah, question, Sarah?
If any of those values were equal to 0, would you still have to do the first 4, so you do 5?
Yes, so good question, right? So it does specify here, find the first 4 non-zero terms of the Taylor polynomial, all right? Because really those zero terms don't really help us at all, they just kind of disappear. I mean, I guess they do, I feel like they would still help with the approximation, or at least keep the approximation more accurate. But anyway, yeah, if any of these turn out to be 0, right, if any of our values here turn out to be 0, we'd have to kind of keep going, okay? Because it doesn't specify n, it doesn't specify, the number of terms of the Taylor polynomial, right? I just assumed it was going to be 4 because, well, none of our function values here ended up being 0, so we could just say, aha, we get our first 4 terms. Although I guess, now that I'm thinking about it, we didn't probably have to, if we wanted the first 4 non-zero terms, we probably didn't need this last one. Because there would be your 1, 2, 3, and 4 terms right there. That's interesting. Well, I'll leave it the way it is right now, but I believe, again, first 4 non-zero terms, it should just be these guys then. I would think, yeah. So, I'll ask about that. I'll ask about that one. All right, so we'll do the same thing here. We're going to now do letter B, so write the 4th degree Taylor polynomial for g. Okay, now g is defined differently. G is equal to f prime of x about x equals 2. Okay, so that's a bit of a weird thing. G of x is equal to f prime of x, but let's not worry about that right now. Let's just focus on, again, setting it up here. So we're writing now a 4th degree Taylor polynomial. So now listen, clearly we're going to go up to degree 4, right? Okay, so that is clear. We're going to use the right number of kind of steps here. So what's our first term going to be described as? So okay, I'm holding off on that just yet. So it will be -3. You're right. I'm going to write it as g of 2 though first. Sorry, I'm doing the more general thing, and then we'll get into that. But yes, the first term will be -3. That's right. So but g of 2, okay, and then it'll be g prime of 2 over 1 factorial plus g prime prime of 2 over 2 factorial x minus 2 squared, g prime 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 of 2 over 3 factorial x minus 2 to the 3rd, and then g, well, 4th derivative of g of 2 at 2 over 4 factorial. X minus 2 to the 4th. Okay. So very good here, right? We don't know too much about g except it is the derivative of f. So g, right, that first thing there, that's equal to f prime, right? And then g prime, what will it be equal to? F double prime, right? And then g prime prime will be f prime prime prime, 3 primes, right? G prime 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 will be f fourth derivative of f, and then the fourth derivative of g will be the fifth derivative of f. Okay, because g is f prime, so we keep taking those derivatives and we'll just keep following along with one another. And we're going to evaluate all those at x equals 2. Okay, you all correctly identify g equal to f prime at 2 would be -3, right? Because we know f prime at 2 was -3, so then g, which is equal to f prime, will also be -3. Okay, which means then g prime will equal what? 6, and g prime prime will equal -12, and g prime 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 will equal 24, and then fourth derivative of g, -48. Okay, because we're following this idea here that the next derivative of f, right, will be -2 times the previous derivative, which is the same thing for g, since g is just, also kind of like equal to the derivatives of that there. Okay, it's going to follow that same procedure. And so you guys are right. G of 2 is going to be equal to -3, and it'll be 6 over 1 factorial of x minus 2, oops, minus 12 over 2 factorial x minus 2 squared, plus 24 over 3 factorial x minus 2 to the third, excuse me, minus 48 over 4 factorial x minus 2 to the 4th. Okay, and again, that is an approximation of g of x. Okay. All right, questions on letter B? Questions on letter B? All right, so one more here, okay, that we're going to write out, and then there's two multiple choice for us in the back to try as well, but let's do this one here, letter C. All right, one more thing, our function, a new function now, right, the fourth degree Taylor polynomial for h, where h of x is equal to the integral from 2 to x of f of t dt. So now h is equal to the integral from 2 to x of f of t dt. And again, we're centered still about x equals 2. Okay, so the fourth degree Taylor polynomial is going to be, and again, for h, this will be h of 2, h prime of 2 over 1 factorial, x minus 2, h prime prime of 2 over 2 factorial, x minus 2 squared, h prime 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 of 2 over 3 factorial, x minus 2 to the third, and h, fourth derivative of h at 2 over 4 factorial over x minus 2 to the 4th. Okay, so again, all those pieces. Okay, so we need h evaluated too. So we're going to first figure out what h is. H is the integral from 2 to x of f of t. Okay. H prime then is going to equal what? If h is equal to the integral from 2 to x of f of t, what will h prime be?
F of t.
F of, don't use t though, right? Use f of x. But exactly right. What is that an application of? Second fundamental theorem of calculus. Oh my gosh. Stop, Mr. Widd. Stop. All right. But the next part's easy. What's the derivative of, what's h prime prime equal to? F prime, right? Yeah, the surprise isn't so surprising now. And then we get f prime prime is equal to h prime prime prime. H, fourth derivative of h then is the third derivative of f there. I don't know why I wrote all those x's, but you get the idea. Evaluated at x equals 2. So what is h of 2 going to equal? 1 or 0?
1.
1, 0?
Because it's from 2 to 2, which is 1.
2 to 2, you're integrating from 2 to 2. There's no like area to accumulate there, so it'll be 0. It'll be 0. Okay, it'll be 0. Okay, and then what is h prime of 2? Well, it's equal to f of 2, and what's f of 2? 4. And then h prime prime is equal to f prime. F prime of 2 is negative 3. And then what will the h triple prime be? 6. And then fourth derivative of h, negative 12. There you go. And once you got those numbers, then you're good to go. So the first term is going to be 0. It kind of goes away. Okay, and so then we've got p sub 4 of x. Thankfully, it didn't have us write 4 terms. It just says 4th degree, so we're good to go there. And voila. Okay, so 7 and 8, I'd like you guys to, well, consider there. Okay, peruse. And number 7, okay, and number 7, you are given the Taylor polynomial for a particular function f. Okay? The Taylor polynomial is centered about 0. Okay, so really call this a Maclaurin polynomial too if you wanted to. Okay? One of these 4 tables here gives you the values of f and its first 3 derivatives at x equals 0. Okay, now remember, since our Taylor polynomial here that we are given, this Taylor polynomial, okay, is centered about 0, all right, think about how our Taylor polynomial should match up with f and its first 3 derivatives at 0. Okay, and use that to help you figure out A, B, C, or D, which one's the right one. Okay, and then the second one there, an example, I guess it's still example 7 there. Okay. Similar kind of situation, you're given selected values of a function and its first 3 derivatives. Okay, so f prime, f prime prime, f triple prime at 0, 1, and 2. Okay, and then what is the 3rd degree Taylor polynomial for f about x equals 1? So I'll help you with this table too. If we're trying to center our Taylor polynomial about x equals 1, do we need this entire table? No. Which parts of the table do we not need? The row that has x equals 0, the row that has x equals 2, right? Because none of that information is pertinent to helping us being centered around x equals 1. Okay? So with that, those 2 little clues there for each one, or the clue for each one there, maybe we'll give those a try now. Okay? So try both of those, see if you come up with the answer. Yes. Yes. Good job. All right, well done.
Want to go T minus 2 days? 2 days until we're they're all happy or all sad. For the SAT scores.
We get out in 2 days.
Yeah, we go on Thursday.
Have you taken?
Thursday. Yeah.
Yeah, so what I did, I actually built the polynomial using the equation, right? So
I did it sophomore year as
You're going down Thursday.
All I need to get is a 13. For what?
This one?
Trying to get higher on the last score. What's your last score? Did you get it?
Yeah. Trying to get.
Have you taken it?
I want to see what Y gets. Because we got the same score.
no questions.
I don't know, I took a sophomore year. I remember in the math section I had no clue how to do something because we just like had it.
The only one that I struggled with were the ones in the English section. Where could this sentence go? Or like, so I was like,
Right, these are simplified.
Good. See, if I were to go on that score, I would have to be taking it.
One factorial is one.
I have to keep taking it until I get a good score.
One factorial is two factorial is
Princeton wants me at 1350. If Princeton wants a 1350, I'm very sure I can get a 1350.
bro, if only I was
It's really zero factorial.
100%. 100%. Hey, all it takes is 1 year of good film, and you're set. Just start. Just start.
Two times one is
I guess a lot of people, remember Coach Stein, there's always like Coach Stein said there's always that one person that ends up helping the team that like you don't see.
good. Yes.
I know, I tried to tell Stein if he didn't play linebacker, but he's like, no, he's playing DN, and I was like, Coach.
I don't even remember how to do this.
So it's you start with the number and then multiply by every whole number down to one.
Are you gonna start him at the end?
So if it's like 3 factorial, 3 times 2 times 1. Exactly.
It's not linebacker, I'll just trade him.
Exactly.
He's like,
Okay, so C and B is what you should get there. C and B. Okay.
DNA?
DNA.
See what I did there?
I do see what you did there. Any questions?
Got it.
I like that.
No, thanks. Alright, any questions? Oh, Cal, come over then. I'll post the homework to do class if you want to get started. You do have like a little over 10 minutes. And I'll be right there, Ariana, then.
I think you're like just pulling into the space or something, but you were quick.
Oh, because I had to go around the light. So I pulled through and then
I'm like driving forward and I just like look back and I'm like, this is so good.